The final chapter of our universe may have just been rewritten. For generations, the scientific narrative has pointed toward a single, chilling conclusion: a slow, cold, and eternal dissolution of all things. This was not mere speculation, but the logical endpoint derived from our most trusted model of reality. That story, the one we've told ourselves for decades, is now facing a challenge so profound it threatens to unravel the very fabric of modern cosmology. The cornerstone of our cosmic forecast, the mysterious force known as dark energy, appears to be behaving in a way we never anticipated. I'm your host, and on this channel, Winds of Thought, we navigate the vast landscapes of human understanding. Today we stand at the edge of a potential paradigm shift, examining evidence that suggests we might have misunderstood the ultimate destiny of everything that exists. We are not just talking about tweaking a minor equation, we are confronting the possibility that the engine of the cosmos is fundamentally changing. Our story begins with the standard model of cosmology, known as lambda cold dark matter, or the lambda CDM model. This is the foundational framework for everything we know about the universe's history, from the first moments after the Big Bang to its projected future. At its heart lies a critical, and until now, largely unchallenged assumption that dark energy is a constant. Designated by the Greek letter lambda, this enigmatic component is not a tangible substance, but a property seemingly woven into the vacuum of space itself. It represents over 2/3 of the entire energy density of the cosmos, an invisible protagonist driving the plot of the universe. This constant dark energy leads to one inescapable finale: the heat death, or Big Freeze. Imagine a future stretched across trillions of years. The relentless acceleration fueled by dark energy pushes galaxies apart until they vanish beyond one another's cosmic horizons. Star formation ceases as raw materials are spread impossibly thin. Existing stars burn through their fuel and die one by one, leaving behind cold remnants, black dwarfs, neutron stars, and black holes. Even these titans are not eternal. They slowly evaporate over incomprehensible timescales through Hawking radiation. The universe expands into a vast, dark, and profoundly lonely void, where the temperature uniformly approaches absolute zero. All structure, all energy gradients, all potential for work or change is gone. This has been our gospel, the cold, logical conclusion written into the mathematics of a constant lambda. But a startling new question now echoes through the halls of astrophysics. What if lambda is not constant? What if the driving force of cosmic expansion is itself evolving? This is not a minor philosophical query. It is a direct challenge to the model's core. Recent findings, from the most ambitious sky mapping project ever undertaken, suggest this might be the case. The Dark Energy Spectroscopic Instrument, or DESI, has provided data that paints a different picture. By creating an unprecedented three-dimensional map of millions of galaxies, tracing the large-scale structure of the universe across billions of light-years, DESI allows us to measure the rate of expansion throughout cosmic history with unprecedented precision. When this map is combined with other pillars of observational cosmology, the ancient afterglow of the Big Bang known as the cosmic microwave background, the standard candles of distant supernova, and the subtle warping of light from gravitational lensing, a tantalizing and consistent hint emerges. The data suggests that dark energy's repulsive push might have been stronger in the distant past, and is perhaps weakening as the universe ages. Think of it not as the engine shutting off, but as its power gradually diminishing. The cosmic acceleration is still happening, but the rate of that acceleration may be slowing down. This subtle shift in the behavior of dark energy, if confirmed, would send shockwaves through theoretical physics. It forces us to consider a universe with a far more dynamic and unpredictable destiny. The comforting, if bleak, certainty of the Big Freeze is replaced by a spectrum of possibilities, each with dramatic implications. To fully appreciate the weight of this potential discovery, we must journey back to the moment dark energy was first thrust into the scientific spotlight. For most of the 20th century, the prevailing view was that the universe's expansion, discovered by Edwin Hubble, was gradually slowing down due to the collective gravitational pull of all the matter within it. The grand cosmological question was whether there was enough matter to eventually halt and reverse the expansion, leading to a big crunch, or if the universe would expand forever at an ever-decreasing rate. In 1998, two independent teams of astronomers using distant type Ia supernovae as cosmic distance markers aimed to measure this deceleration. Their findings delivered a stunning surprise. the supernovae were fainter and therefore farther away than expected. The only plausible explanation was that the expansion of the universe was not slowing down at all, it was speeding up. Some unknown repulsive force was counteracting gravity on the largest scales. This discovery, which earned its leads the Nobel Prize in Physics, was christened dark energy. Yet, naming it did not explain it. To this day, the true nature of dark energy remains one of the greatest mysteries in science. Is it a cosmological constant, a fixed energy density intrinsic to empty space as Einstein once proposed, and later discarded? Is it a dynamic field, dubbed quintessence, that varies across space and time? Could it be a sign that our theory of gravity, Einstein's general relativity, breaks down on the scale of the entire observable universe, requiring modification? Or does it point to the existence of extra dimensions or other exotic physics beyond the standard model? Dark energy is a placeholder for our ignorance, a mathematical necessity born from observation that resists a clean, physical explanation. Its assumed constancy within the lambda CDM model was a practical simplification, a necessary assumption to make the equations tractable and the predictions clear. DESI's data now threatens that simplifying assumption, opening a Pandora's box of theoretical possibilities. Let us delve deeper into the mechanics of this discovery. DESI's power lies in its ability to perform a galactic census on a monumental scale. Mounted on the Mayall telescope in Arizona, it uses 5,000 robotically controlled optical fibers to capture the light from 5,000 galaxies at once, analyzing their spectra. A galaxy's spectrum reveals its redshift, the stretching of its light toward longer, redder wavelengths caused by the expansion of the universe. By meticulously measuring the redshifts and positions of tens of millions of galaxies and quasars, DESI constructs a 3D map of cosmic structure. Crucially, within this map are frozen sound waves from the infant universe, known as baryon acoustic oscillations, BAOs. These BAOs act as a standard ruler. By measuring the apparent size of this ruler at different epochs in cosmic history, scientists can calculate how fast the universe was expanding at each point in time with extraordinary accuracy. It is a direct historical record of the expansion rate. The preliminary analysis from DESI's first few years of data, combined with other datasets, indicates a deviation from the prediction of a constant dark energy. The expansion history we observe seems to fit better with a model where dark energy's density decreases over time. The statistical confidence, while not yet at the gold standard of 5 sigma required for a definitive discovery, is significant and provocative, hovering around the 99.99% level depending on the combination of data. In the cautious language of science, this is strong evidence, not yet proof. It is a signal loud enough to command the attention of the entire field and redirect the focus of future missions. If this signal is real and dark energy is indeed dynamic, the consequences for the ultimate fate of the cosmos are dramatic. The simplistic dichotomy of freeze or crunch expands into a nuanced spectrum. Let's explore the scenarios that unfold from a weakening dark energy. Scenario 1. The coasting universe. In this model, dark energy weakens to the point of becoming negligible, but never reverses into an attractive force. The universe's expansion, having been accelerated for billions of years, simply loses its driving boost. Gravity, while still too weak to halt the expansion, remains the dominant large-scale force. The expansion continues forever, but it transitions from an accelerating phase to a steady, constant-rate expansion, or even a gradual deceleration. The end result is still a cold, dark universe, but the timeline is drastically altered. Structures like galaxy clusters, which were doomed to be torn apart in the classic Big Freeze, might remain gravitationally bound. While star formation would still eventually cease, the epoch of cosmic structure and light could be prolonged. The universe would die not with a frenetic rush into isolation, but with a long, slow sigh. Scenario 2. The rebounding universe, the Big Crunch. This is the most dramatic alternative. If dark energy not only weakens, but its energy density becomes negative, essentially transitioning from a repulsive force to an attractive one, it would add to gravity's pull. In this case, the acceleration would not only stop, it would reverse. The expansion of the universe would slow, halt, and then begin to contract. Galaxies would start moving toward each other, their light blue shifting as space itself shrinks. The contraction would initially be gentle, but over billions of years, it would accelerate. The cosmic microwave background, now a cold whisper, would heat up, first to room temperature, then to the temperature of stars, and beyond. The night sky would grow brighter and hotter as all the photons in the universe are compressed into a smaller and smaller volume. Eventually, galaxies would merge, stars would collide, and space-time itself would become searingly dense and hot. The universe would potentially collapse back into a singularity, a mirror image of the Big Bang, known as the Big Crunch. Whether this singularity marks an absolute end or a potential rebirth into a new cyclic universe is a question for speculative cosmology, but the process itself would be utterly catastrophic for any conceivable form of life long before the final moments. Scenario 3. The Big Rip Alternative. It is worth noting that a weakening dark energy is not the only alternative to a constant one. Some theoretical models have explored the opposite, a dark energy that grows stronger over time, a scenario phantom dark energy. In this terrifying model, the repulsive force becomes infinite in a finite time. The acceleration would become so violent that it would overcome all forces holding structures together. First, galaxy clusters would be ripped apart, then individual galaxies. As the end approaches, stars would be torn from their orbits, planets from their stars. In the final moments, even atomic and nuclear forces would be overcome, and every molecule, atom, and subatomic particle would be shredded by the expansion of space itself. This Big Rip represents a fundamental disintegration of space-time. While the current DESI data does not point toward this model, its existence highlights how profoundly our cosmic fate depends on the subtle behavior of this unknown component. Beyond the cosmic fate, a dynamic dark energy would force a seismic shift in our understanding of fundamental physics. The Lambda CDM model is not just a story about the universe's beginning and end. It is the framework used to interpret virtually every cosmological observation, from the formation of the first galaxies to the distribution of galaxy clusters today. If its foundational parameter is wrong, a vast array of measurements and derived values, the universe's age, its total mass energy content, the curvature of space, could need recalibration. It would strongly suggest that dark energy is not a simple cosmological constant, but a dynamic field, reviving theories like quintessence. This, in turn, could provide a crucial link between cosmology and particle physics, potentially pointing to new forces or particles that operate on cosmological scales. Furthermore, it might provide the crucial evidence needed to develop a modified theory of gravity that can explain both the motion of galaxies and the accelerating expansion without invoking an unknown dark energy component. The stakes could not be higher. We are potentially glimpsing entirely new physics beyond the standard model and general relativity. The scientific community, true to its nature, is responding with a combination of intense excitement and rigorous skepticism. The next 5 years will be critical. DESI continues its 5-year survey, with more data that will refine its measurements and increase the statistical significance of its results. But it will not be alone. A new generation of observatories is coming online, designed specifically to probe the dark energy mystery. The European Space Agency's Euclid Space Telescope, already in operation, is creating its own ultra-precise map of billions of galaxies to measure cosmic expansion and the growth of structure. NASA's Nancy Grace Roman Space Telescope, launching later this decade, will perform wide-field surveys to discover thousands of distant supernovae and map the distribution of matter through weak gravitational lensing with phenomenal depth. On the ground, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will repeatedly scan the entire southern sky, discovering millions of transient events like supernovae and tracking subtle changes in the cosmic web. This multi-pronged, multi-observatory approach is essential. Systematic errors, subtle biases in data analysis, or unknown astrophysical effects could mimic the signal of evolving dark energy. By attacking the problem with different instruments, different techniques, supernovae, BAOs, weak lensing, galaxy clusters, and different teams, scientists can cross-verify results. The goal is to either converge on a definitive, reproducible detection of dark energy's evolution, or to rule it out, sending theorists back to the drawing board. This is the scientific process at its grandest, a global collaborative effort to test the very laws we believe govern reality. For humanity, this pursuit is about more than just satisfying curiosity. It speaks to a fundamental desire to understand our context. We are not just passive inhabitants of a predetermined cosmos, we are conscious beings capable of observing, measuring, and reasoning our way toward an understanding of the universe's grand narrative. The question of whether the cosmos will end in ice or fire, in silence or in catastrophe, is perhaps the ultimate question of context. The answer shapes the meaning of the cosmic story in which we are fleeting participants. Does our narrative lead to an eternal quiet oblivion where all structure and memory are lost? Or does it point to a dramatic cyclical story of birth, death, and possible rebirth? The psychological and philosophical implications are profound. Furthermore, the technological and theoretical spin-offs from this research are immense. The challenge of processing the petabytes of data from DESI, Euclid, and Rewritten drives advancements in big data analytics, machine learning, and distributed computing. The need for ever more precise instruments pushes the boundaries of optics, detector technology, and aerospace engineering. The quest to explain dark energy, whether as a field or modified gravity, stimulates breakthroughs in fundamental theoretical physics that may one day find applications we cannot yet imagine. As we await these future revelations, we find ourselves in a uniquely thrilling moment. For the first time since the shocking discovery of cosmic acceleration in 1998, we have compelling, observationally driven reason to question the simplest explanation. The universe, in its infinite complexity, seems to be whispering a secret that contradicts our textbooks. The familiar forecast of a big freeze is now under review. The haunting specter of a big crunch has re-entered the realm of legitimate scientific discourse. Before we conclude, if unraveling the deepest mysteries of existence excites you, if you believe that pursuing these questions is a noble and defining human endeavor, then you are in the right community. Your engagement fuels this exploration of ideas. Help us continue this journey by hitting the like button and subscribing to Winds of Thought. Your support is what allows us to delve into these grand narratives and share them with you. So, we stand at a cosmic crossroads, looking at signposts written in the light of millions of galaxies. The data is a compelling hint, a suggestion written in the fine details of the largest map ever made. The coming years will transform that hint into either a revolutionary new truth, or a fascinating false alarm. Either outcome will advance our understanding. Either way, the quest continues, the relentless, beautiful human drive to comprehend the story of which we are a part. What do you think awaits us in the unfathomably distant future? A silent, eternal winter where all energy fades, or a final, fiery reunion that gathers the scattered cosmos back into a single point of infinite potential? The universe holds its answer close, but for the first time in a generation, we are asking the question with fresh eyes and new tools. Share your vision for the ultimate fate of all things in the comments below.